Well, we'll be talking about the implementation of virtual function in this class. And in our last class, to summarize the last class that we have discussed, so this will be the topic of today's class: virtual function under the hood, and mainly it is implemented through through two basic items. One is virtual table and virtual pointer. We'll see what it means. Before doing that, just a couple of minutes of what we did in our last class. We talked about virtual function and polymorphic types. Any class that is having at least one virtual function will be called as a polymorphic type class. And if you use virtual function within a class, in that case, if we try to invoke that function using a function pointer, a pointer or a reference to that object, then it will trigger dynamic dispatch or dynamic binding. And uh, in case we have got such classes in a hierarchy, we call it as a polymorphic hierarchy. And we also found that if we have virtual functions in a particular class hierarchy, then it is recommended that we have virtual destructor also included, because otherwise it might lead to object slicing of the derived object. And it may not. So when we try to deallocate or delete the object through the base pointer, if the base pointer was pointing to a derived object, then it will be partially deleted and the derived portion will remain in the memory that we found. So that is called object slicing. So for that, virtual destructors are required. So we found the use of virtual function, virtual destructors. So now we'll see how this is actually implemented internally and what the compiler does, or what internally the compiler implements to make things dynamic and to create the magic of switching either to the base function or the derived function automatically. So as we see that if we have a polymorphic class, then the compiler internally creates for each polymorphic class, it will create a virtual table or virtual method table as we call, and we use the notation, abbreviation as vtable. For the virtual table, we call it as vtable, and corresponding to that particular class. Just okay. So this, so what we mean is each class will have its own vtable, and what the vtable will contain, it will contain the addresses of all the virtual functions that particular class is having. So how a class can have its virtual functions? Either through inheritance, it will inherit a virtual class from its base class, or it can be explicitly declared, a new function can be explicitly declared as virtual. Okay, and accordingly a particular class can have multiple virtual functions. So this vtable is supposed to have the addresses of all these virtual functions, and so it's basically a array of function pointers you can think of. And so this is what it means. It creates the internal virtual table, and it is addresses of all the virtual functions, the array of functions. And all the virtual table function addresses are laid out in some order. Say if we have declared the virtual functions first the f1 and f2 then f3 in the class, you may expect that in the virtual table also you have first the address of f1, then the address of f2, then the address of f3 is saved. Okay, so table address 0 will have the address of v1, table address 1 will have the address of f2, and followed by f3. And another point is, whenever you create an instance of that particular class, as many number of instances that you create, so each object will be using in some form, we'll discuss it about it. So each object of that particular polymorphic class will be referring to that particular virtual table that belongs to that class. So in some sense, all objects belonging to a particular class of a same class will therefore typically share the v table. So v table will have a single copy, and each object will somehow try to, through some uh, variables, we'll see, it will try to link to that uh, virtual table. Now how it is done? Now the compiler places an additional pointer called virtual pointer. So this virtual table and virtual pointer, these are all hidden kind of items that you find, and the compiler internally does all these things and generates a code for it. So the programmer need not have to do, and that's why from the programming, from when you run the code, you find that something magical starts happening as dynamic binding, but this is actually uh, done by the compiler to take care uh, of this nice thing. Okay, so the compiler places the additional pointer which is called a virtual pointer, and this virtual pointer is a special kind of pointer which is will be storing the address of the virtual table of that class. Okay, so if a class has got two objects defined, so each object will have a virtual pointer, and both virtual pointers of the objects will be pointing to the single v table. We'll see that in a diagram in the next slide. Okay, now the point is, in that object layout, apart from the variables data members that we define, we'll have this new pointer member also added. So where the pointer member will be stored, will it be in the top of that object layout, or it will be bottom? So that there is no hard and fast rule defined. There's in the C++ standards, there is no mandate of where to be this to be implemented, but and compilers implement it in some form, like G++ previously placed the VPTR at the end of the object. Okay, so we'll also show it accordingly. And there is one VPTR for each object. So each object will have one VPTR, which is a simple inheritance. Simple inheritance means the particular class is derived from one base class. We are not considering multiple inheritance right now, which is a kind of special case, or there are certain more things to be discussed for multiple inheritance. So right now we are talking about simple inheritance, and here one VPTR for each object is enough. And so the point is, every object when it is instantiated will have internally, automatically it will have a virtual pointer, but this virtual pointer need to be initialized to the virtual table's address. So where it will be done? Definitely during the construction of the object. As a result, some additional code regarding something like VPTR assign the address of vtable need to be there in the constructor, need to be added in the constructor, which is a hidden code to be added in the constructor by the compiler. So if you have not declared a specific explicit constructor for that particular class, then the default constructor that the compiler provides will have this code. If you have written additional constructors for that particular class, so each of those constructors will have this extra code added, and the compiler will read. The programmer need not have to bother. Okay, so once the class is having a VPTR with a array of function pointers to each of the virtual functions, and the object is created of that class having a virtual pointer initialized to that virtual table, now the things are ready. So through that function pointers, if this example, so all through the virtual functions, if we perform, like this is a base pointer, say for example, assigned to some object's address, which is either a base or maybe derived, and through that p, if we invoke a particular method, say f1, so normally we write this, but the compiler internally will translate this to something like this. So what it does, it will translate it to something this, and it has got some kind of dereferencing of the pointer variable, and then accessing the functions code and all this. So we discuss about it later in the next slide, but this is how this translates. So there are three things done. The vtable is created to be shared by all objects. Each object will have one additional pointer, which is also initialized in the constructor. So these are all hidden. At the same time, whenever you make a call to a particular virtual function through the pointer or reference to the object. Okay, so then the code gets translated to this. So these are the three things that internally takes place to make things happen, this dynamic binding happen. So there is one more point that we'll discuss later regarding the overhead of implementing the virtual pointer. So in the next slide, we'll see the example, one simple example, which is having a base class B, and it is having a derived class D. If we look into the base class B, then we find that we have a data member B1, entire data member, but because we have got some virtual functions, this class will have a virtual table also. At the same time, so this is a virtual table for that particular class. At the same time, internal to this class, there will be, you can think of that VPTR is defined. The VPTR is a pointer to vtable type. So this is also a hidden code that gets inserted as if a new member to this new data member is getting added to this class definition. So once this is done, as you can see, this class will now contain in the object layout of this class, any objects that you create will have we need to have the space corresponding to B1 and also VPTR. It's a pointer type and it's integer type. Okay, it says something like this. So a class, the object of a type class B will have entries corresponding to B1 and also corresponding to this VPTR. This we mentioned in the previous slide. And as we mentioned also that in the constructor, we have not mentioned any explicit constructor or destructor because we just want to focus about how the translation of call to a virtual function takes place, considering VPTR and vtable. So we have not mentioned the constructors or written the constructors explicitly here. So still there will be default constructor, as we know, the compiler will provide, and in that default constructor it will have a initialization code where this VPTR gets initialized to the virtual table. Okay, so I just mentioned it as because these are the things that the compiler does internally without the programmer's intervention. So here this is there, and then we found that there are two virtual functions. One is fv1 and fv2, and say let us assume that in the code segment, because all the function bodies are stored in the code segment and the local variables are stored in the stack segment, the dynamically allocated objects are stored in the heap segment. So in the code segment, this is the body for fv1, this is the body for definition and the body for fv2. So the function body is there, and the starting address of that entire piece of code for fv1, that is stored in the virtual pointer in the virtual tables first entry, because virtual table is nothing but an array of function pointers to each of the virtual functions corresponding to that class. So for that fv2, we have stored the base address of that function here. So this is the address of fv1 and address of fv2, and probably you can assume that because fv1 comes first in the definition and followed by fv2, their addresses also appear to be in the same order as it is in case of virtual table. So the compiler will know that it will have some policy of ordering the while it lists the virtual function addresses. Okay, so once this is done, before we come to the D, let us see that what happens when we create or assign when we create an object of type base type and we try to assign it to a pointer to a base class. So BP is a pointer to the base type, and we are trying to allocate dynamically a base address. So when we do this, so it should be, it's a mistake that I made. It should be new B. Okay. So when we have done this, so there's a mistake here also. So when I have done this, that means say this is the object dynamically allocated object corresponding to class B. And let us assume that it is in the heap segment. We are not bothered about that. So when we do it, we find that apart from B1, which has been our explicit data member, we have got space for VPTR also. And this VPTR also, when we construct it, it actually invokes the default constructor. Within that, this initialization is also done. So once it is initialized, this VPTR actually points to the base address of the virtual table. And obviously beforehand, this virtual table need to be prepared by the compiler. So once we do this, if I write bp arrow fv1, that means through the base pointer I am trying to invoke the virtual function fv1. Then virtual function means it will trigger dynamic binding, and to trigger dynamic binding, this will be replaced by this piece of code. So what this piece of code says is bp arrow vptr. So bp is the base pointer. It's just a pointer storing the address of this class object, base class B's object. So this bptr arrow vptr, bp arrow vptr means bp is the address of this. Arrow vptr means sorry, it is referring to this particular member of this object. What it contains? It contains the base address of this table. So if I write this with this index 0, that means I am trying to refer to this one. Okay. So now if I give an asterisk here, this means what? This address means I am getting into that particular location. So I am now accessing the element here, and then accessing the element means I am trying to invoke that element. So this will be the function will be invoked, and what we are doing here is passing bp. Bp is what? Bp is nothing but, because it's a member function, the address of the object is also passed, which is actually pointed by this. So that's why I have written here bp, because bp contains the address of this object. So here bp arrow vptr, once again if I repeat, so this much you are here, you are basically here. When you write here this much 0, that means you are here. Now when you give an asterisk means you are actually here. If you get the asterisk, you are actually here invoking the function. And when you invoke the function, you are passing, because it is void type, so it's getting at least one argument, that is the address of the object, which will be pointed by this, because it's a simple member function. So that's why I have mentioned here. So this actually will trigger the code for fv1 in the runtime, and it will trigger a suitable copy of it, because fv1 in this case it's a base pointer, and also the object type is also the base type. So there is so it's basically invoking the same type of, the method belonging to the same type of class. So now let us come to the, and if we do so, bp fv1 and bp fv2, we'll find that the function body is getting invoked and it's a suitable. So this will actually trigger this one, and this will actually trigger this one. So this we found in our previous discussions, but here we see that how internally the thing is happening. This dynamic binding is happening. Now let us see how this is done when we create a derived object. Again, there is a mistake, as I mentioned. So there's a mistake here. It should be new D. So once I do this new D, so this is the class D's object that gets created, and we see the address we store it in derived type pointer. So this also, there is no change of type. So this is a derived type pointer dp. Dp points to the class object's address, class D's object address. And then if we write dp arrow fv1, so when this is done during the construction itself, we know that as you can see here, before we get into that, when we allocate the space for a derived class, what a derived class is having, it has inherited the b1 that has been defined in B. It has also defined a type, a integer type variable d1. So that's why it has got b of b1 corresponding to the base class, d1 that is defined of its own, and it will also have a virtual pointer because it has got a few virtual functions defined and also inherited within it. And what we found is if b of fv2, this is a virtual function that it has inherited, and in fact it has inherited fv1 also from its parent or from its base class because we have publicly inherited it. But it has decided to override, as you can see, fv1. So fv1 got overridden. fv2, it is using the same copy that the base its base has defined, and in addition it is trying to define a normal function, a non-virtual function f1. So the derived class is having basically three functions. Two of them are virtual, one of them it has overridden after it gets inherited from its base class. The other one, it just uses the base's copy, and it also includes one non-virtual function f1. So that's why, as you can see here, this is the non-virtual function d of f1. Okay, so how many entries will be there in the class d's virtual table? It will be 2 because it has got two virtual functions. So it will be, the point to notice, there will be no entry corresponding to the non-virtual functions because those can be triggered or invoked quite easily and without any complication, because and that actually implements static binding. But because for virtual functions it requires dynamic binding, that's why this v table is there containing array of addresses corresponding to the virtual functions corresponding to that class D. So here the point to note is if v1 it has overridden, it has its own copy. So that's why I'll have this is D's fv1 and this B's fv1 all in the code segment. So this all these functions will be in the code segment, and you will have two copies of fv1, one that has been written by base class, one that has been written by the derived class. So here, because in the derived class is having its own copy, so it will be pointing to its own copy, and it will expect whenever you invoke fp1, this copy should be invoked if you are invoking through derived class object type. But fb2, it has just inherited and did nothing, so fb2 will be using the same copy that the base has written. So that's why this fb2's address points to this b's fb2, and this points to this one. So once this is done, now if I call fb1 dfb2 df1, so dfb1, what we see, dfb1 will be translated to this address, and in that case dp arrow vptr, that means you are here, then 0, that means you are here, then asterisk, that means you are getting access to the function, so you are here, and asterisk of this means you are trying to invoke or execute the function. It is not accessing a data variable, it is executing a function. So this function will be executed, and you are passing the dp, that is the object's address, which will be pointed by this. So this is what it means. So once you do this, you will get this executed, okay, and it will have this display in the output. When you call dpfp2, it will be all the same. It will come to vptr, it will be translated to, and this ordering will be maintained by the compiler. It is 1. The second address, this is this, will take it to this, sorry, it will take it to this, and it will display b of fv2. So this is quite normal because it has not its own copy. It will just expect the base's copy to be executed. And df1, it is non-virtual, so there is no such changes. It will simply use static binding and simply make some statements in object code that you should call this particular. So a call to this address, it will be explicit, whereas here it is implicit. I mean, it has got some additional extra code, extra referencing and all, dereferencing and all. So as you can see here, the override of executing a virtual function and So in this case, fv2, I mean this one you can think of that will be executed this one. Okay, fv2. So what I mean to say is virtual function, it has got some additional code that need to be, or additional overhead to get to the VPTR, and from that we collect the function's address and then dereference it, then call it. So it will take some more time, some more overhead. So you can expect that virtual functions, if we use it, we get some flexibility. By the same time, we have some additional overhead and it might slow down the system. So that is also there. But static bind, it is all simple. During the compilation, you can put the address where the function is, and it is basically uh, it's bound in the runtime in the compiler. Now comes the, so this will trigger, I mean this will trigger this d of f1. Okay, so now let us see if we create, or I mean if we assign the class d's object's address into the base pointer, so something like upcasting. So if we do this, like the dp, it was pointing to this one, so the contents of dp, so this value I am putting it here in bp. So I'm putting these contents here. That means what? BP will also point to the class D objects. So now this is allowed because it actually implements upcasting. Okay, upcasting. It's too difficult to write. So it's upcasting, and upcasting is valid. So through this upcasting, this base pointer is now pointing to the derived object. So if I write BP arrow fb1, so then what it will do? It will be translated like this. So this translation is straightforward, and through this translation, what you do? Through this BP, you get into the VPTR, and then through the VPTR 0, you means you are here, and then asterisk means you are actually here. So that means even if you invoke fb1 through the base pointer, now you can still get this derived classes fb1 getting executed. And this is happening because you are not directly triggering, you are accessing through the virtual table corresponding to that function, corresponding to that object, which is actually pointed by the VPTR as a part of this object's layout. Okay, so because of this and these internal say items, this dynamic binding can work, and it can trigger a suitable function type. So the idea is, whenever you have a dynamic binding, the body of the function will depend on the type of the object that the base pointer or the pointer is pointing to. Not, it will not depend on the type of the pointer that it is having. Okay, so that is happening. So this one will trigger here. In this case also, this will trigger this copy, although you are invoking it to the base pointer. And this fv2 will definitely trigger this basis copy, because the derived class is not having its own fv2, and in fact that is also recorded here. I mean this fv2 is actually pointing to the base classes copy. So one last point regarding this is, now can we write this like bp arrow f1? So bp, if I would like to invoke this, so bp is a base pointer. So base pointer knows that there is no, because it knows that how to access the items which is common to the base and derived class. So f1 is exclusively defined in the derived class, and which this base pointer is not supposed to know, because it's a part of derived implementation, and the base pointer is not supposed to know all this. But so if you, so that's why if you write bp arrow f1, definitely it will be a message. But now, as we found that sometimes in C++ we can make explicit casting, explicit type casting. So if we cast this bp, which is actually a base pointer, the contents of the base pointer as a derived class object's address, if we explicitly typecast and then we write arrow f1, then which is not very common, because I mean generally how you come to know about this information. But if we somehow know this, and if we can do this, this is basically forcing to implement downcasting. So downcasting is not possible, but we can force it. We found earlier. So this is not common. So this is not implicit, but we can explicitly force it to happen. And if we force it to happen, definitely then B of F1 also can be displayed. That's true. But knowing this, that what this BP should be typecasted to, it's not easy to know. I mean, it's not, so for that it is not easy to know that what BP is actually pointing to. Okay, and if that is not known, we don't know what will be this casting. Okay, so we because BP is a base pointer, and the base pointer might have different hierarchies of derived classes. So now which one it should be casted, it's difficult. But there are some mechanisms to get it done through say runtime type identification, RTTI, and all this. We can discuss about it later on. Okay, so for the timing, we can ignore that. We can kind of somehow ignore this, and we can fairly assume that okay, this may not be required. And finally, if we just write this, that means we are trying to create one more derived type object. Okay, so and assigning it to DP. So now what happens? So this is one more time. This was the previous one. This was the outcome of this was. So this was the outcome of this object. I mean this call, and this is creating this object. Now once this is done and DP is pointing to it, so DP earlier pointed to this, now DP is now pointing to this. Now you see the point that there are two objects of derived type. Now both the objects are having their own VPTR, as you can see here. But because they are all D-type class object, so both the VPTRs will be pointing to the virtual table of class D. So each class will have one single V table, and any number of instances that you create, object instances, through their VPTR, they will all point to the same table address, okay, through which the virtual function calls can be resolved for, I mean, whenever we invoke it through that object's address. So this is a point to know. Okay. Okay, so before we end this lecture, I just try to summarize that as we found that the compiler internally creates for each polymorphic class, it was for the class B and D, it has created virtual method table or V table, one for each class, and the V table is the same for all objects belong to the same class. In the last slide, we found that two objects of class type D is sharing the same virtual table, and there is a VPTR which is a part of the object of all objects that we create of polymorphic type, and there's an initialization code in the constructor which actually initializes the VPTR to the vtable's address. So this is internally done, and in our example also we have shown that maybe the VPTR is actually placed in the bottom of that object layout in all the cases. And we have also found the I mean meaning of why this translation actually works and enables us to implement or to exhibit dynamic dispatch. And finally, as we find here, that the virtual call incurs additional overhead, and that is indeed true, because if you have a virtual function call, then it gets translated to this. There will be 2 or 3 dereferencing operation and all, so it will take some more time. And a simple experiment shows, an experiment done in 96 indicates that approximately it can be at most 50% overhead gets increased at some point of time. So if we need virtual function, definitely it is fine. Otherwise there is no point of adding additional overhead to the code that we execute. So this information I have copied from the wiki page of virtual function and VTable. So this is all about how virtual functions are implemented. And when we say it's virtual function, we include virtual destructors also. So no matter what is there, if you just have a virtual destructor and no other functions declared as virtual, then also you will have one VPTR, and the VTable need to be maintained and all this. And it is always recommended that if you have got a class which is inherited from a base class, and you are allowing upcasting, then it's better to have virtual functions declared and a virtual destructor declared. So this is for this particular class. In the next class, we'll be talking about another topic, that is pure virtual functions and abstract base class. Okay. So that's the end of this lecture.